that's mrs_jwebinar28.ipynb. And just the introductory bit of the notebook is where you find the GitHub link and just sort of some descriptive background information. Okay, so this is the first cell where there's some importing happening, definition of paths. Here are where the data is, both the input and output directories for each of the two observations within the program, observation 3, which is the science data, and observation 4, the dedicated background data. Both input, where the underscore uncal.fits data is located. That's the raw data that is the input for the stage 1 part of the pipeline. So specifying where that input data is, and then specifying where the output data from each part of the pipeline will go. Here's the part from the slide where you can specify the channel and the band. So here we're doing the short wavelength channel, that's MIRI IFU short, and then working here on the medium grading setting data, so the medium band. The way we've kind of constructed the notebooks, you can toggle on or off whether to do different parts of the pipeline. So here, toggling whether to do detector 1, spec 2, or spec 3. And here we want to go through all of them, so we set them all to true. Doing the whether to do background subtraction, or whether to process the background data, sorry. And in this case, we're doing that. You'll notice that you get the choice of 1 and 2, but not 3, because in 3, all of the data is used. So it assumes that you've already processed the background in stages 1 and 2. Another section where we're toggling what sorts of background subtraction to do. So here we're not taking advantage of the pairwise subtraction that you get from the stage 2 part of the pipeline. That would be what we're calling, or what is called here, the pixel-based background subtraction in spec 2. But we are doing the master background subtraction in stage 3, so that's set to true. If there's no background folder, ensure we don't try to process it. Okay, so that's to do with the backgrounds, but we do have backgrounds here. Okay, more import statements. Identifying the pipeline version in CRDS context. Also defining that we're saving the intermediate output, or the output from the intermediate levels of the pipeline, in addition to the final output at the end of stage 3. So we have those paths here for both the science target and the background. You can even keep track of how long it's taking to do all of this. There's a cell for that. Okay, so here is where the way that you call the detector 1 part of the pipeline, here's where you can set that. And so you can set the keywords for individual steps in the pipeline. So here we're specifying where we want the output to go. And so it's this outdir, which I think goes back to the paths that we set up here. So outdir will be one of the things that's called in when you run that part of the pipeline. If we wanted to skip a step, you could uncomment here, for instance, like skip for whatever reason last frame. I don't know. There's a good reason to do that. Just showing how to do it, and then you set that equal to. You would set it equal to true, that you would want to skip the step, but we don't want to skip anything here, so all of this is commented out. Here is where some of the keywords for a couple of the steps are being set. So here for the jump and ramp fit steps, we're setting certain keywords, and these all pertain to the correction for cosmic rays. So cosmic rays, sometimes we can get them abundantly for the MIRI observations, and we kind of refer to those as cosmic ray showers. So it can be very important to do a good correction for the cosmic rays. So this is an example where it is important to try perhaps different, setting these values differently and seeing how it reduces the data. So going back and doing reprocessing. For the rest, we're kind of keeping everything pretty much the same as the defaults, and we do want to save the results. So that's how how we're going to call detector one, the detector one part of the pipeline in this notebook. And the next step, it identifies and counts up the files to reduce for the science observation, and it says that it found 4 files. And then the next cell, it actually does the reduction of detector one for the files. So here you'll notice in pink you get this very verbose output. Every now and then you'll get white, and I think that's where there's a print statement explicitly defined in the previous cell, where we define the run det one that defines how we want to run detector one. So this is, in this case, it's just identifying which file that it's working on. And so you get this verbose output that's kind of default for the pipeline, tells you everything that's going on. If there were an error and the pipeline crashed at some point, then you'd see the verbose output would go to a certain point, and then you'd see the traceback messages that you get that lets you kind of do the trace what it was that was an error. Okay, so in this case it processed everything successfully, and then we have to do the same thing. That was just working on the science data, so you do the same thing for the background data. That's the next cell here, and here it finds 2 files that for the background data, and then so it does the same thing. Run the same function run det one on the 2 background files, and that's the verbose output here. And again, there weren't any problems. Made it all the way through. You can see how long the data reduction's taking with these time commands that are interspersed throughout the notebook. Okay, after that, so now we've processed through the detector one pipeline. So the input for detector one was underscore uncal.fits files. The output will be underscore rate.fits files or underscore rateints.fits files, for at least for the IFU data. And so we work with the underscore rate.fits files. So here, after running detector one, in preparation for spec 2 part of the pipeline, if this is where you would create the association file if you needed it. For instance, if you were going to do the pairwise, pixel-wise background subtraction in spec 2. So for instance, this is where you would specify the specific background files that you would use if you were going that route. But in this instance, we're doing only the master background subtraction. Let's see, and then keeping track of which files there are. So again, 4 science files, 2 background files. Here's where we define the spec 2, how we run spec 2 on the data. And so let's see, again, specifying the output directory, what happened. This is accounting for the way that we can tell it to either toggle on or toggle off the background, the pairwise, pixel-wise background subtraction. So based on what you set pixel underscore BG to at the top of the notebook. Looks like here we're leaving a lot of it alone. for the pixel replace step. So this is a step where if you have a bad pixel and it happens to land, say, on top of the trace of your point source, or perhaps in the middle of of an emission line for an extended source, then it can create a nasty divot in your spectrum, in the output spectrum. So the pixel replacement algorithm can help with that. Here we're setting the skip keyword for pixel replace to false. So we don't want to skip this step, and we're implementing the min-grad algorithm, and I think that tells it how to do the interpolation to find the replacement value for the bad pixel based on the surrounding pixel values on the in the slope image. And then here, if we've specified whether or not we want cubes, then you can tell it to turn on or off the cube build and extract 1D steps. Sometimes it's important to look at the output 1D spectrum or the cube that you get from Spec 2. That, remember, that's only processing, that's calibration processing done only on a single exposure for all of the exposures. So if there's something that doesn't look right in the very final product from stage 3, then maybe something went wrong in one of the exposures, but not the others. And so it's useful to look at the cube or the 1D spectrum from Spec 2. But if you're not worried about that, it can take a lot of time to run cube build, although there have been improvements on that. And so you can save time by turning off the cube build step. If you turn off the cube build and extract 1D steps, you still get another output where the file name ends in _cal.fits, and those are the inputs that are specified in the association file that is called for the stage 3 part of the pipeline. So you'd still get the _cal.fits files, even if you turned off the cube build and extract 1D. Okay, so we've defined the Spec 2 function call, and then this is the cell that actually does that. And so you can specify it to run on the association file, but if you're not doing pairwise subtraction of images to do that option for background subtraction, then you can just run this on an individual file in Spec 2. So again, verbose output, this was successful. That's just for the science data. So again, another call for the background data, and then the verbose output, successful run, and then you can keep track of how long it's taking. Okay, so those are the first 2 stages of the pipeline for MRS, and then now stage 3. So first a note that when you get data from, when you get cube data, you're getting data in surface brightness units, so like megajanskis per steradian, not flux units. So if you were going to just go to the cube yourself and sum up the signal at each of the slices, each of the wavelength slices, then you'd have to remember to multiply by a conversion factor that goes from the surface brightness to the flux units. And there's a keyword in the header, pixr_sr, that can be found in the SCI extension header, and that would be used to convert from the surface brightness numbers that you would get to flux density. And so I guess I should have pointed out, so the data files that you'll get will have different extensions, and each extension will have a header with relevant information. So that, like, the first extension is typically the science data that you'll be using to extract the spectral signal from. And then there are other extensions like the uncertainty extension and the data quality extension. I'll get into the data quality. I can show you some examples in the NIRSpec notebooks. And depending on the level of depending on whether it's raw data or output from stage 1 or stage 2, you get different extensions. And there's a link here to read the docs. So this is a lot of information on the pipeline. So here, like I followed the link for CalWeb Spec 3, and there's all sorts of information. Like here at the top, it gives you a breakdown of which pipeline steps in Spec 3 are covered for the different instruments on James Webb. So if, like, for instance, for MIRI MRS, it's going through most of the steps here. So read the docs can be a very important resource. Okay, so again, Spec 3 requires an association file. And extract 1D can works differently depending on if the source is a point source or an extended source. When you design your observation in APT, there's a point where you define the source itself, and there's a drop-down menu where you select whether you say that it's a point source or an extended source, or if you don't know, and I think the option is unknown. That information actually gets propagated through the headers. So if you said that it's a point source, then it'll get propagated through. There's also a step in the pipeline that can determine if it's a point source or extended source. But depending on whether the data product, once it gets to extract 1D, has an indication that it's a point source or extended source, that affects how extract 1D extracts the spectrum. So if it's a point source, that's when you get the aperture photometry. That's the aperture and then the annulus for the background. And then if it's an extended source, then you get extraction from the whole field of view. So you just keep that in mind. So here's a step where we create the association file that will be used as the input for stage 3. And so here, like, you'll notice this is where you would specify the background files. And so it'll indicate all the files that it should consider. And then this is just keeping track of how many files there are. Again, 4 science and 2 background. And then it makes the association file. Here is where we define in the cell how it runs Spec 3. So again, specify the output directory. Again, we want to save the results, accounting for our ability early in the notebook to toggle whether or not to do master background subtraction. So here is what I was talking about earlier, the outlier detection step. If you were going to experiment with it, say that they had made some changes recently and you wanted to experiment with it, then here you could do that and set individual keywords for the outlier detection step to different values, and then try the reduction and see how it looks, and then maybe adjust as necessary. There's the output type keyword that I mentioned in the slides for cube build, and set that equal to band here. And the IFU _ autosend, and then also specifying that we want the 1D algorithm for residual fringe correction that is part of the extract 1D step. Okay, so that defines how we do the function to run Spec 3, and then this is the cell that runs it. Here's the verbose output, and there were no problems in the extraction, so there's no traceback error. And then here's the, if you want to keep track of time, how much time it took to run, there's that command. Lastly, just plotting up the results. So the output files that you'll get from extract 1D are _x1d.fits. That's the extension you'll get at the end That's the very end of the file name, underscore x1d.fits. The output that you'll get from the cube build step is underscore s3d.fits. And so here, this is just plotting up the spectrum. So you remember that for this, I did the data reduction just for the short wavelength detector and for the medium grading setting. So that gives us the 1B and 2B parts of the 1B and 2B bands. And so 1B is I don't know, about 5.6 microns to 6.6 microns, and you can see the spectrum for that segment here. And then the 2B is like 8.7 to 10.2 or so, and you see that segment. And so that's the end of the MRS notebook.